So really go ahead if you have any questions, because like I know on the engineering part I might have been fast. Maybe I'm going fast here, so just feel free to stop me, because otherwise I'm gonna be done in 1 hour. Okay, so as I tried to give you like an intuitive reason of why we're using some well-localized wavelets, we have shown that thanks to the good localization property of the wavelet, the modulus combined with those, so actually it's called an analytic wavelet, combined with those analytic wavelets, is smoothing the envelope of the modulus of the convolution. There is one more property which is slightly more tricky to prove. It's the fact that if you take a zero average filter, it's going to almost commute with deformations. So the proof is in the seminal paper about the scattering transform called Group Invariant Scattering, so by Stefan Mala. And so I will not present the proof here because like it's really tricky. But like, so given those two properties, one can wonder, okay, so what can I do there, right? So I'm quite invariant with translation. I'm stable to deformation. And what I mean by stable, it's really this idea that you're Lipschitz with respect to variability. The way, like, the more stable you are, and of course, the smaller is the Lipschitz constant, right? So what's important here is the Lipschitz constant, because everything is, in some sense, everything is compact or infinite dimension, so normally you're Lipschitz with respect to anything, right? So what's very important is the amplitude of the Lipschitz constant associated to any Lipschitz property, okay? So, and I think I got again another slide about that, but I'm going to insist about like this phenomenon. How to address deformations. So the simplest is to, again, try to be Lipschitz with respect to deformations. If you're Lipschitz with respect to deformation, then you are Gato differentiable. If you're Gato differentiable, then you know that you're going to linearize approximatively your deformations. And in this case, the simplest way to build an invariant, and that's really the appropriate word to create an invariant, is to do a projection. And the nice thing is that the linear invariant can adapt, can be adapted to the degree of invariance which is needed for a given task. So for example, like, just to be clear, because it could be like, okay, I want to be invariant to any deformations. Makes no sense. Why? For example, 6, 9, 1, 7, so in the American way to write it, if you're invariant to deformations, you will not be able to distinguish them. So it's pretty crucial to be just stable, and that the invariant can be adapted to the structure of the signal. Everybody got it? Okay. So now we have the wavelets. So the most natural operator to design is called a wavelet transform. So I'm pretty sure everybody is familiar then. And okay, so the proof is in the slide. So I mean, the intuition is in the slide, so we don't really need it. But, so the way the wavelet transform is designed is via the Littlewood-Pelley property. And so what you try to achieve with the wavelet transform is to be an isometry. So how to be an isometry? So assume you're given a collection of wavelets. And I'm going to write an approximative property in the Fourier domain. So it does, okay, I'm going to write f omega. Okay. Yeah. So, sorry. So that's the little Hood-Perry property. A way to think about it, so there is those high-pass filters, so the wavelet, and of course there is a low-pass filter. So why am I saying of course? Because what you see here is basically this equation there on the blackboard. So each wavelet filter is dilated, which so a dilation space corresponds to an inverse dilation in the Fourier domain. And so, and the low-pass filter is needed because otherwise there is, since every wavelet has a zero average, there is no way that you can capture the zero frequency, right? So you necessarily need a low-pass filter. And so you're going to adjust your wavelets, so basically some Gaussians, such that this constant here, epsilon 0, is as small as possible. Ideally, you would like something that's going to be an isometry. Because if you have an isometry, so all your problem is way better condition, and also you're sure that you're covering the full wavelet, pardon, the full frequency space. Okay. So if you're working in a compact space in Fourier, then you can hear, it's not going to be 1, it's going to be like 1 over a certain domain, and you can restrict this property to a smaller domain. And if you want to get this norm of the W, so I will use this notation widely, so with the W here, you need to really get this formula. And so the way to do it is like, here I'm going to multiply by the norm, pardon, the squared of the Fourier transform of X, everything in the equation. Okay, I'm going to remove the omegas, or rather, sorry, it's not going to be. So if you're confused, ask me, like, it's going to make everything simpler. Here we got the square. Here we got the square. And so what do we do there? This is a isometry property, right? So we get that X factored by 1 minus epsilon 0 is smaller than and so this I'm going to call it, so the full thing here is going to be like Wx, so this is its square norm. Here it's going to be like I'm going to distinguish the low frequency from the high frequencies. So that's going, so there is a J. To always like remember that we work with a finite scale. Squared, this is going to be my low pass filter. This is a square norm, and you see that you have approximately an isometry. And so, so that's how you define a wavelet transform. So you observe that here the sum is over some finite indexes, right? So it's not something continuous. You can work with a continuous wavelet transforms, it's fine. But here we prefer to work with a kind of frame. So the L2 norm is well defined, and you see how we go from the spatial domain to the Fourier domain. So it works in 2D. I mean, okay, I'm more a vision guy, so I work in 2D, but like you can do that in any dimension. So if you remember the property before, we said that a single wavelet is stable with respect to deformation, which implies that Vj is stable with respect to deformation as well. Just the constant will be huge because it will be a function of the number of filters you will be using. Well, it's clearly covariant with the action of translation. I hope everybody's convinced, right? Okay, nice. And as you might know, this is what typically people use. So for example, in the class yesterday or 2 days ago, this is what people typically use to express their signal, right? Okay. So now we go to the scattering transform. And so what's a scattering transform? It's Cool. It's a cascade of wavelet transform and a modulus nonlinearity, and all the coefficients are average. So I'm going to formalize everything. And I think the cleanest way to think about it is as follows. So I'm going to try to write as big as I can for people online. You get an input signal X, okay? So you want to create an invariant. What do? So if you remember what we discussed before, like we said that with a simple averaging, we're going to get an approximate invariant with respect to the translation. So what we do is, all right, I'm going to apply aj on that, and I'm going to get ajx. This is by what we're going to call the zero-order scattering coefficient. It's simply an averaging. Okay. But then, if you just do a sum, whatever is the support, there is a loss of information, right? Because you're completely ignoring a whole spectrum of the a whole array of the spectrum in the frequency plane. Okay. So what you do is that you apply the Vj operator, the wavelets. This is the low pass filter. A for averaging, W for wavelets, and V, I don't know why. Right. Then on Vj, we're going to apply a modulus. Why would you apply a modulus? Because there are two reasons. First of all, if you apply no modulus, your representation is linear, right? So it will not be very useful. Second, aj Vj is approximately equal to 0. So if you apply again an averaging on those coefficients, we get something close to 0, right? Everybody's following and agree? Okay. And so you need to think in terms of Fourier space, and so maybe, yeah. So just to, I'm just going to add this slide because it might be helpful. So blue is aj, red is Vj, and Wj is the whole wavelet. So this is great. So here we get the modulus of Vjx. And here, how to get an invariant with respect to translation? We average. So again, you apply aj, and we get S1x, sorry, equal modulus of Vjx, right? So there is something, so I don't know if it's, okay. So with that, you get the first order, the first order of the scattering transform. Yeah.
Yeah, it's just a silly question. Why do you use the modulus as a nonlinearity?
So I'm going to go like into the details, but like if you remember what we discussed right before the break, so I should not have done. Yeah, it's fine. If you remember like what we discussed before the break, if you apply the modulus on the convolution of a signal with a well-localized wavelet, you get something which is more stable with respect to translation. Why? Because if those two guys are approximately close, then it means, because one is translated, that it's more in the low frequency domain. In other words, you're not going to create some high frequency oscillations, and so in this case, it means that you're smoothing your signal, thanks to the modulus. Thanks for asking. Sorry. So, so we apply this modulus because actually it's going to put more energy in the low frequency domain while preserving the energy of the signal, right? Because we have the fact that x squared is approximately equal to the square norm of the wavelet transform, which is equal right? So it means that along this cascade, the energy of the signal is preserved. And the modulus will act as a demodulation, nonlinear demodulation. Then, what can we do again? The same thing, right? So we apply Vj, and okay, you get that this is this is like Vj applied on each coefficients, each signal from this vector, and then you get Vj of Vj. Oh gosh, I'm really a mess. Of Vj of x. Great. What do we do again? We apply an averaging, and you get the second order coefficients. And what can we do again? We can iterate this idea. So we will need to prove like that the remainder is going through 0, but actually if your wavelet is smooth enough, you can prove that this is going through 0. I kind of prove, like, thanks to the preservation of the energy here, that actually Sx this is an isometry, right? It does preserve the energy, and this is preserved because the cascade is itself preserving the energy of each signal. And we have approximatively the invariance with respect to translation, right? Everybody sees it, why? Because like there is the averaging here which is applied. So we have this nice tree structure which allows to build a nonlinear operator which is stable to translation. And which has some very nice sparsity property, stability properties that we're going to discuss now. So what you see here, so okay, I took a random picture, and I apply like the, I'm showing you like the first order scattering coefficients. So, no, so first of all, there is averaging, right? So it's just the smoothing of the signal. Then you see, so I honestly don't remember how the wavelet coefficients are distributed. Like what you see is that there are different orientations and different scales which are represented here on this signal. And most of the signal is sparse. So why is it sparse? Because first of all, the wavelet decomposition has this tendency to be sparse itself. And despite the averaging, if you average a lot of small coefficients, one can see here that it remains sparse. Yep. Oh, sorry. At each level of the transform, we apply the same Vj and the same Aj. Yes, absolutely. At each level of the transform is the same wavelet transform which is applied. And the J is a parameter which is fixed, which guides the degree of invariance that you want to get with respect to translations. Well, I hope I am answering to David. Yeah.
Do you have to use the same wavelet transform at each layer, or would it make sense to change for some specific purpose? For example, in audio application, people don't use wavelet that much, but they use iterated filter banks, which are more Gabor-like, but they change the shape of the filters at each layer.
So you can completely play with that, and you can go even like, so I'm going to present even something a bit like more complex. We can even change the group over which you're going to integrate. So the framework is pretty flexible. It's just that if you want to be sure that you're going to get the nice properties, for example, like stability, energy preservation, it's always good to write explicitly the tree to be sure that there is nothing which is lost when you're adapting your transform to the specific signal you're studying. But yeah, you can do anything, almost anything. Well, right. So, okay. So I was discussing deep learning right before, so which is something where you're learning every layer end to end. Oh yeah, there is a question.
I hope it's not again a silly question. So you compute the wavelet transform of the detail. So you convolve the modulus of the detail coefficient, and so this seems that it's not the same size as the original image. Or is there a downsampling procedure?
Okay, so this is an excellent point. I'm going to discuss it later, but like as you know, wavelet have those localization properties. So indeed, to avoid redundancy for speed reasons, when you're going to practically compute it, you can downsample progressively the signals. The only signals that you do not downsample, but I think people in signal processing are used to that, is the first wavelet transform. You keep it always at the full resolution because like otherwise there is too much aliasing. But that's, just from the perspective of practical implementation, actually, if you try to implement it yourself and you do not put enough oversampling, you see that you're losing something, like by simple visualization like that. Well, but you're right, yeah, there is a downsampling factor by 2. So, and actually I'm going to discuss that more precisely in this slide. So, if you consider like an orthogonal wavelet transform, which is basically such that this becomes an equality between the norm of X and the norm of the wavelet transform, which implies that you can find a basis, an orthogonal basis that can be dilated on L2. I think you guys are familiar with wavelets, so you must know that. So if you get like orthogonal wavelet, then you can have access to what is called a conjugate mirror filter. And from the conjugate mirror filter, if you start with your initial signal and you propagate through, so I'm going to write that. I forgot there is a blackboard behind. Sorry, bad habits. Yeah. So if you propagate like a filter, so I'm doing it in 1D here because it's for the sake of simplicity, but the extension to any dimension is straightforward. So the idea is to have a filter H and a filter G, this is 0, this is 2 pi, with the appropriate randomization. And this is squared, so that both of them sum to 1. So if you get those two guys, and you propagate them, your signal through the cascade of those filters, followed by a downsampling, you get something which is a bit similar to what we discussed right before. So I think you begin to get that there are many trees behind wavelets. You can implement the fast wavelet transform, and actually you can, the equality is formal if the wavelets are orthogonal. And this is great because, like, right before the break, we were discussing like neural networks, where everything is trained end to end. And actually, the scattering, there is something that does not flow well because, it does not respect the architecture of standard neural networks in the way it was. But actually, there is a very nice point of view where you can view the scattering as a CNN. So I'm fixing my, so theta here is an angle because I was working in 2D. So if you fix your H and your G theta, this is how you would implement a wavelet transform. So according to your question, there is an oversampling on the first layer, which is standard signal processing, and then you downsample progressively your signals. So the reason is because here we're working with Gaussians, and Gaussians, Gabors, they're not an orthogonal basis, an orthogonal wavelet basis. Thus, you need to have some approximation. If you're working with orthogonal wavelets, of course, there is no need for the aliasing. So from that, we can define a scattering transform. So here, how to do it. So first, I'm gonna get any intermediate signals. You're going to apply the same filter bank to each of those signals. So this is stupid, right? Because j times h is approximately equal to 0 from this equation here. So we're going to add some modulus in between. Great. And so h is positive. And then we're going to remove the modulus, so at every time that we meet a h. And I'm going to get rid of some filters. And what you see here is actually an implementation of a second-order scattering. Why? Because the combination of, basically there is this idea that if you convolve for two scales, so that lambda 2 is larger than lambda 1, to get the first x of psi lambda 1, you're going to iterate lambda 1 times the low-pass filter. Then you get a j on it. And there is this assumption that actually if you apply the modulus is going to smooth the signal, if you remember what we did with the wavelets. So we're going to assume that applying the modulus on this cascade is not going to change much as a result, the resulting output. And so what we do then is that we cascade lambda 2, so I'm going to write this, minus lambda 1 h. We again apply a g, take the modulus, and this is approximately equal if when you apply with the assumption that when you apply the j with the appropriate downsampling, x convolved with psi lambda 1 downsampled lambda 1 times will be approximately equal to the, with the modulus, will be approximately equal to the envelope of this guy, right? So if you do it this way, then you have a very nice implementation of the scattering transform with conjugate mirror filters. So in practice, it's absolutely not used. The reason is that there are too much aliasing, and so you prefer directly to implement the scattering with Fourier transform. It just like, it doesn't work. And that's how you get the orders. So you can check, like just for a sanity check, we can see that the order 0 is indeed something where there is no modulus, and it's only like light blue stuff which are extracted. For the order 1, we see that the signal is only going through a single nonlinearity, and for the order 2, there are two nonlinearity. Everybody sees? Okay, cool. All right. So scattering is a sort of CNN with appropriate filters. So I'm not saying that any scattering neural network is exactly a neural network. However, it's very close. So how do you get stability to deformation? So I had a question right before, I think it was you. So if you apply, so the wavelet approximately commutes with deformations, but actually, the low-pass filter is achieving invariance. I mean, of course, approximate invariance with respect to deformations. And so I was just writing explicitly the kernel which is associated to those kernels, to those operators. So you see that if you apply a deformation to the signal, so given AJX is simply a convolution, so you get the right term. And for the left term, well, just apply alto on the output of the signal so that you get this nice kernel. And so the way you can achieve stability with respect to deformations is by bounding appropriately the kernels. Actually, if I remember well, you apply 2 times the Shor lemma on integral operators, and you get the bound. It's pretty straightforward, as far as I remember. And so, as I said, this bound on the wavelet transform is a bit changing, but like there is a very naive way to do it. Is by you first get it for a single wavelet, and then if you have j wavelets, then you will get j times the Lipschitz bound with respect to deformations. So if you remember the slide with the stability to the modulus. And so how do we prove that we get invariance for the order 1 scattering? So I mean, stability for the other one scattering. So we have AJ, VJ, L2 of X. I don't even need to write X. Yeah, no, I do not even need to write it. So we want to show that this is small. So how do we do? Someone has an idea? Well, so this is equal to this guy minus this guy plus and I'm lucky because I did well. So you see what's going on now? No? So it's a very naive bound. It can be improved like pretty much because like otherwise it's gonna. I mean, you can use a tree structure to improve the bound I'm going to show. So it's more or less an intuitive bound rather than something formal. So the first term it's AJ of the Lie bracket of VJ alto. Right? Oh, it's very dirty. Second term, it's I did some terms, sorry. And the second term is, so I did an extra sum, it's not useful, sorry. And we should apply VJ, sorry. So the top sum is equal to this guy. So actually, so this you can bound it with the bound there. So. And this, because Vj is an isometry, I mean, is the one Lipschitz, sorry, Wj is an isometry. Can get that. And this guy is going to be smaller than, okay, there is a C prime. Okay, and so if you think about it like in signal processing, the Jacobian of the deformation is going to be dominant compared to the constant term, like, I mean, the infinite norm of the tau. Because, like, basically it's a translation term. So, you know, I mean, it wouldn't make sense if the stuff was infinitely translating itself. So we have, yeah, and I did the mistake here. This is fine. So we have, like, stability of the order 1 of the scattering. So if you want to do the order 2, you can iterate this idea. So I'm sorry, like, there is a mistake here, but this is fine. This term is not good. So you can do it for the order 1, the order 2, etc. So the big issue here is that it's not a great bound, because if we sum over all paths, the Lipschitz constant is going to diverge, right? Because, you know, there will be an infinite amount of paths. And so if you sum an infinite time those stuff which are constant, then you're going to get something that is going to diverge. However, if you use the tree structure in a nice manner, you can get a Lipschitz bound which is finite. Actually, this is a very elegant proof that Stefan Mada has done in the invariant group scattering paper. Right, so if we summarize the properties of the scattering transform, what do we get? So we have something which is one Lipschitz. Everybody get why? Because we cascaded only Lipschitz operator. Modulus is non-expansive. Wavelet transform is non-expansive. So at the end of the day, thanks to the nice tree structure, you get an operator which is one Lipschitz. So then, if you neglect the tau term, you get the fact that the scattering is Lipschitz with respect to deformations. This is great. So I didn't prove it, but like, of course, AJ is approximatively stable to small translation of amplitude smaller than something that depends over power of the scale J. I hope everybody is convinced. It's just like, standard signal processing. And something a bit tricky, it's covariant with group actions, which means that if you apply a rotation or a translation, of course, to your signal, it's going to get reflected in the index of the coefficients. In other words, if I rotate my image, I will rotate the wavelets, and so the translation is shifted in the index space. And then don't worry, I'm going to be more formal. But for now, let's get it this way. In other words, the scattering, the 2D scattering, is covariant with the action of Euclidean groups. So the previous properties are super nice for standard signals classification, like for example, small digits or these kind of things. But you can also do it for textures. And the main property you're going to use, so you take a stationary process, which is, I think, the simplest way to model the texture. It can work in 2D, 1D, or whatever you want. And the property that is mainly used is the fact that the expectation for some probability space, which is well defined, is commuting with the action of translation. And actually, the reason why is because it's a linear operator, continuous, so you can both commute, right? Okay. And so this leads us to the expected scattering. So instead to have an averaging, you take the expectation with respect to your signal. And since averaging and expectation commutes, what do we get? Oh, sorry. What do we get? The fact that actually the standard scattering is a non-biased estimator of the expected scattering. So note that the modulus is super important here, because if you do not apply the modulus, the expectation of a zero-sum signal is going to be 0. Right? So, voilà. And if you're a bit familiar, so I think it was like 2 days ago, no, yesterday, there was a notebook that was discussing the power spectral density, and so basically you recover the fact that the energy of the signal is preserved across the expected scattering. Pardon, the order 2 moments of the signal are preserved through the expected scattering. So it's super nice, because you get again an operator which is isometric. You have a way to characterize stationary process, which are actually images. You can imagine anything in the texture around us. So it's pretty useful. So great. Now question: does it work? Yes and no. So there are tons of papers. If you follow the group of Stefan, so I was one of his PhD, but there are many papers of the scattering, which is applied in various directions and on various data sets and various type of signals. But I guess one of the most successful, so it was prior the LXNet and kind of things, it was on small digits, MNIST. And so in this case now, I hope you got a good guess of why it's working pretty well here. It's the fact that there is the only variability here corresponds to geometric variability. Translations, deformations. Once you remove them, all the problem is a problem of sample complexity. It's going to be the same with texture, so I'm going to discuss that a bit further right after. So except that for textures, there's also this idea you would like to be invariant to rotation. I mean, in particular, those guys there. So all the variabilities are known. There's also the scale. So the scale is a bit tricky to manipulate with the scattering, but I mean, it's the same in audio because it's not exactly a group. The fact to change the scale of a signal, like there are some issues with the model. So you cannot really do a convolution along the scales, but like there's some way to handle scale variability. And so the design of the scattering transform is guided by a Euclidean group. And so in this case, you get state of the art on those tasks. On the other hand, they are super trivial. I mean, MNIST is a bit known to be. I mean, that's one of the first exercises you're going to do if you do a machine learning class and this kind of thing. So, well, and if you apply the scattering transform on ImageNet, I mean, on large data sets and this kind of things, I swear to God, I tried a lot, and I think there's still a work in progress, and hopefully one day it will work, but like, it's not yet. So, can we extend this kind of things to other type of groups? Because like what you've done until now is just the translation groups, right? So RD, basically. But everything which is done here could be extended to there. There are some like tricky things if you want to go to 3D, because if you think about it, like in 2D, there is this nice property that you can get a finite approximation of the circle. Like for any epsilon, you can find a finite subgroup on the circle, which is approximating the rotation group with distance epsilon. This is not the case in 3D, for example. You can prove that any finite subgroup on the sphere will not cover SO2. So it means that if you want to extend it to the scattering to 3D, there is a bit of work to define an appropriate wavelet transform. But still, so the notion of conversion, you can extend it in a pretty straightforward manner, at least on Lie group. And measure.
I have some question. Can you address also the case of graphs? Because maybe you have also this notion of convolution of graphs on graphs.
So I got like 2 students who are working on this question. Who are here. And the answer is yes. The thing with graph, to me, the answer is a bit complex with graph. And the main reason is that many people have based their intuition to develop, for example, GCNs on graph Laplacians. And if you think about it, the issue with a Laplacian is the fact that it's going to be isotropic, which means that you're never selective to a specific orientation, and any eigenspace of the Laplacian will be a circle, right? Because it's a circle. And so the fact it's a circle means that you're not going to be selective to a specific orientation. And the intrinsic reason is the fact that it's very hard to define in the real Laplacian, you have access to a Fourier transform. And Fourier, because like translation are going to commute with the Laplacian, and from that you can derive you can get the specific eigenspace of a specific orientation. But in the case of a graph, if you push this energy in 2D, in 1D it works pretty well. In 2D, you don't know what's a good basis of an eigenspace. So in this case, everything is a bit arbitrary. You're doing stuff, but like there is no, it's not well defined. So yes, we can extend those techniques, but I think there is still a bit of lack of understanding, and like it's probably the main issue is the fact that we don't have an accurate model as we have for MNIST or textures, for example. So hope it's answering your question. Okay, so if you take a Lie group or a compact group, you can define a Haar measure. And so you can have access again to a notion of square integral functions. And if you have your square integral functions, taking the invariant measure, you can define a notion of convolution, which is like, it's literally straightforward. I mean, if you work by analogy with the Euclidean case, you get those formula. You can verify its covariant with the action, the left action. of translation, not the right. And it's pure group with commutatives, it works. And there is a notion of like Fourier analysis also, which is possible to do. So it's a notion of characters. So to be precise, you take a section along the eigenspaces of the translation. But like a nice way to view it is like, if you consider the L2 norm of this is an isometry, J gives the translation of signal by J, which means that you will get like a symmetric operator, and then you can diagonalize it, and you have access to several eigenspaces. And with those eigenspaces, you have access to a notion of Fourier. So it's possible to manipulate like Fourier transform even on complex, more complicated groups. And one example that I really do like is the rotor translation. So if you have a notion of convolutions on two groups, extending this notion on the product of group is straightforward. To a semi-product of group, quite straightforward. And so one group I really like, so it's what I'm discussing here is based on the PhD of Laurent Siffre. It's the fact that this is a non-commutative group, the rotor translation group. Because if you think about it, if you translate a vector and you rotate it, so the same thing as rotating it and then translating it, right? Yeah. So the operation is defined by that. Super. So let's assume that you got y, which is parametrized by u and theta, and psi, which also depend on u and theta. Okay, so it's going to be a speed question. Who can tell me the explicit formula which is there? So you got like those two filters. We know the group operation. So has someone an idea of what is done there? Nobody? Maybe? No? Well, so if you compute the inverse and then you make the product with the inverse, you end up on this. And I don't know if you remember the structure of the scattering coefficients, but like there is something which is a bit similar. It's this idea that here there is a rotation. Here it looks like kind of the standard convolutions, and here, okay, everything is normal, that's fine. Okay, theta here is a nice variable. U, not really. So, you can iterate like the standard scattering. So let's say you want to build an invariant rotor translation group. Sorry, I'm going to get it. So what do? So you have like the averaging, which is invariant, right? Well, you do a change of variable, it's going to be stable to the rotor translation group. This is great. Then if you get the first layer, there is not clearly a rotor translation variable that is appearing, but almost, because like you got θ1 and J1. And actually, if you make like the rotor translation group acting on your signal, then you see that there is a notion of covariance, so you need to average along angles here. If you do not average along angles, you're going to rotate. So rotation here corresponds to a shift of your coefficients, of the index of your coefficients. And so you really need to average along the angles. But that's really too bad, because if you remember the structure of the tree, zero order it's nice, first order it's nice, but like we really would like to get, to something more subtle. And if you get back, like if you take like the formula that there was before, it's really similar to what you would do, like a second convolution over these coefficients, as if it was separable in space and rotation, except one thing, the theta prime here. Right? And with that, you get some non-trivial invariance, because there is this idea because of the fact that you have a non-commutative groups, you need to kind of shift, and actually I'm going to think I have a visualization. You need to kind of shift your coefficients. So you get some s the x, which is again invariant to roto-translation. And you have this, I find it beautiful, like there is this idea that you're going to convolve your signal with rotated wavelets. And in fact, you need to apply them, to rotate them progressively with a shift to get the appropriate invariant with the roto-translation group. And the way to think about this is like, okay, if I apply a roto-translation to my signal, is it indeed covariant? Is my representation here indeed covariant? And if it is, if you remember some slides before, then an averaging along the roto-translation variable will build an invariant. So you really want to be covariant with the action of the group. And thanks to the fact you use this convolution, you get the covariance, and then you get the invariant. And you could cascade this idea again and again to more complicated group. So there is sort of hypothesis behind that, which is a symmetry hypothesis. So there is this very nice paper by Stefan Mella, it's called like Understanding Deep Convolutional Neural Network. And there is an idea that to each classification task, there is a symmetry. So this just exists by, it just like any physical problems, like there's always a group of symmetry which is associated to the group of physics. So for example, if you have a classification problem, it could be just the fact to permute the samples which are in the same class, right? If you think about it, like this is a group, because it's just a permutation, and it preserves the level set of the classification task, right? So you always have access to this group. However, it might be a bit high dimensional. If we had the group, the problem is solved, because then you know everything, basically. So instead, for the sake of simplicity, because it's very hard to go beyond linear algebra when you're doing some applied math, you can hypothesize that there exists a Lie group, which, a sequence of Lie group, for which you need to be progressively more invariant. And when you will get this progressive invariance, and I hope this makes echo with the previous, remember like the second section of my talk, you really hope that you're going to get something that will stabilize progressively the different classes, right? But it's a hypothesis. And so one simple example, it's of course R2, and then the roto-translation group. And then you could add like the Euclidean group, because we could also add the symmetry, right? The actual symmetry. We could add the scales, we could add like any more complex group, but like the issue is that, what's next, right? I don't know. What is beyond Euclidean structure on the signal? I don't know. Maybe on audio signal we could know, but like for images it's really unclear. And so one way to think about that, it was like some work we did with a kind of generalization. So each time you apply a convolution, you agree that you add a new index. And this index corresponds to the filter bank, which is applied to your signal, right? So we're not performing again a convolution along this new index. And if you want to get an invariant, because here you explicitly build the group of invariants, you just average, right? Everybody catch it, or like, see everybody with a suspicious side? So imagine you're given some layer xj that depends upon like vj variable. What do? You apply a new filter on this vj. You get a variable vj plus 1. Great, this is your new layer. At some point you need to end up the fun. And what do you do like to get the invariant with respect to all those high dimensional convolution? You just average along each orbit of the layers, right? And so if you average, you get the invariant, and you have explicitly built the group that is supposed to, if you solve the problem, that is supposed to preserve the classification task, because you just translate along one of the variables, going to translate everything. What is a bit unclear is what's happening if you translate in the first layer and the second layer, but still, there is this notion of translation, which is here. So it's only for a commutative group here. So call that an attribute. And so right now I'm just opening like the literature of equivariant CNN. So it has been, I should have put the reference, which has been developed by Max Welling in particular. So the work is like several years after the one of Stefan, but the main difference is the fact that they are learning the filters, which is a bit similar to this idea here, because here you can potentially learn the filters. The thing is that you explicitly write here is a group of invariants, which is a bit different. And getting the group is always way more difficult than getting the filters along the group. If you think about it, like just estimating a two-dimensional group, it's a giant matrix. And if you have a giant matrix of size n by n, you need at least n square coefficients. You see that it becomes quickly pretty untractable, right? Well. All right. So we're done with this section for like the invariance. Neural networks. So I should say invariance in the scattering networks. So my goal was not to claim, and that's really a disclaimer, I'm not claiming that neural networks work like the scattering transform. That's not my point. My point is to give some tools to try to interpret, to have some intuitions on what can be possibly do by the neural network. It's pretty rather different. I would never claim that, for example, I show you some initial filters of the LXNet. That looks like wavelets in some sense. I would never claim that the next filters are wavelets. Not only it's not true, I mean, not only it's difficult to check, but also I'm pretty sure it's not true. Which does not mean that potentially you could find some wavelets on some good groups that would allow you to build invariants. The question is open. All right, so let's go a bit like in the statistical results. So there are several lines of results which are a bit super exciting. So so if you so you guys you're pretty familiar with machine learning tools. So there's one of the first things you want to do to analyze a new machine learning tool is definitely to employ the risk decomposition. So what do? So you have like your you have the expected risk. So you have never access to this one, but like on the other hand, you have access to the empirical risks. So this is great because what can you do? So I know there are some. You can decompose in many manners your risk, but my point is to have like 3 terms. Sometimes you can have 2 if you're interested in implicit bias of the optimization, but that's not my point. You have like 3 terms. You have an approximation error. So it's basically if I get a solution with my empirical measure, how far it is from the best solution I can get. So you could, of course, take Fn instead of F. I mean, like there are many variants. I'm not claiming it's the best way to decompose the risk. It's just one way, which I think is helpful for getting intuitions on what is important to study this tool. There is the estimation error. It's going to be like, hey, if I got an accuracy on the training set, how good is it going to be on the testing set? And then there is optimization error. So I'm not very familiar with it, but like basically it's like, okay, if I optimize my stuff, how far is it from the solution I would love to get? And if you're in a non-convex world, I don't think there are many, tools to get a good estimation of this quantity. So we're going to I'm going to present you several results through this scope of like approximation, generalization, and sort of optimization results, right? So, and you might be interested. So I remember, like on the first day, I think there was some talk like about the Belking double descent effect. So I'm not discussing that. Yeah, the optimization landscape. I remember like there was a discussion I think yesterday. Yeah, I think it was yesterday, but whatever. There was also some discussion like, is there a good analogy between proximal operator and deep learning? Yesterday, this is for sure. I will not discuss the best approximation, right? But like, I mean, the literature is so wide. There is almost every day a new paper about like the theory of deep learning, and everybody is claiming every day that he's solving the deep learning, blah, blah, blah. And so it's so wide that it's very hard to be extensive. But like, there are several works I really do like, so I would like to introduce you to them. So, the German way is so there is a Reinbacher complexity, which is so let's start by estimation bound. So because like there is this funny thing that it actually does not work at all, and I want to show you why. So, so you know, I mean, like to one of the simplest complexity bound to understand how your model is going to generalize is to go through the Rademacher complexity. So what you do there is that you're wondering like how good, basically, a way to see that is how good my model is going to be to fit random noise, basically. That's a way to interpret the Rademacher complexity. You can link it to the generalization error. So that's great. But in practice, it's a bit difficult to estimate. So in general, you're going to use a proxy. And one of the simplest proxies is going to be like the VC dimension. So it's this idea that if you have a set of points, oh, okay, there is, sorry for the typo. If you have a set of points, you're going to say that a functional space is shattering this set if you can split it in two power m. So each subset of the set of points can be separated by my function. Oh yeah, by assumption I'm working with real valued neural network. Otherwise, just you multiply by the dimension every bounds and you get the resulting bounds. So that's great because it sounds very appealing. So you can also link the VC dimension to the Rademacher complexity. So that's great. And actually, for a neural network, I know there are some more recent bounds, but like basically you can say that it's going to be a big O in the number of parameters and the depth. It sounds quite reasonable, right? Because in general it's going to be the number of parameters, so something slightly bigger here. Looks nice. But actually, you have this upper bound. And some people, they did observe that, and that's the magic with neural network, if you get the empirical Rademacher complexity, so you always get like a bound with high probability in this case, because it's not an expectation anymore. You can show, and it's very funny, like that a CNN can fit random labels, which exactly mean that this bound is equal to 1. So basically, I'm just saying this bound is vacuous. Too bad. And so there is this nice paper, I mean, I think there is Benjo, it must be like Benjamin Recht on it. So it means that Rademacher complexity might not be the good tool, to analyze neural network. We need to think of something else. And so there is Peter Bartlett, who is like really the specialist of those bounds. So he came up like with some spectral bounds. So here's the idea is slightly different. And I tried to simplify them at the maximum, because like, first of all, we're running out of time, and I just want to deliver like the big picture. But so basically the idea of this bound is that it's going to be sensitive to the product of the norm of each operator of the cascade. And the way to think of it, and actually the idea of the proof, it's like literally because you get a Lipschitz function of those operator, you can use an epsilon covering of each layer, because they are linear operator, and from that you get a bound by actually upper bounding the Rademacher complexity, but you're introducing a notion of margins. So that's actually one of the big contributions of Peter Bartlett, if I remember well, when he was like some years ago. So that sounds super, super nice, and actually it's a very exciting paper. And because if you combine them with margins, suddenly there are some very nice results that do match empirical, and for me it's very important to bridge the gap between empirical and theoretical evidences. So you see that your model, your trained model, is going to be sensitive, so basically to the margin. So the margin is the distance between the real label of a sample and the best second prediction. I mean, if it's not the appropriate one, the best second prediction of your model. And when you renormalize, the distribution of margins, so this is what you see here. You see a distribution of all the margin in your model, and you normalize them in this way. You see, for example, that CFAR random is super difficult, MNIST is super simple, CFAR is, in between. and it allows to quantify the hardness of the data set. So here you could be like, okay, that's great, because we found something which is, it seems to be sensitive, it seems to be working, so it's great. And then actually, you get somewhere else, you're like, okay, well, I'm going to compute everything, my bounds explicitly with the real numbers, and suddenly you end up with, that's all the bounds with margins and with those spectral complexity bounds and recent work. I'm pretty sure some guys have, improved them, and probably there is some order of magnitudes which are better, but like you see, they are gigantic. And they're not doing better than the VC dimension. So there is still some work to do in this direction. Voilà. Right. So that's my take-home message on that, is that it's still very hard to find the reason why they are generalizing pretty well, and to upper bound those generous error in a good manner. And the work is done by actually Nishabo, and that's, if you want to check this kind of bounds, it's really like the guy you have to check his web page. There are many references. Niti has a lot of work on that, and what I really appreciate about his work is that he's always trying empirically to validate his bounds. So this is really great. So now something else, like the optimization of a neural network. 10 minutes. So in deep learning, if you have no extra assumptions, you have like the best non-convex bounds for convergence, which are just vacuous. You write like your potential. You use the fact that it's going to be as smooth under like simplified assumption, and at the end of the day, there is a derivative here. At the end of the day, you just get that you might found a critical point, and without other assumptions, like if your model was behaving like something convex or something else, you cannot get something better, unfortunately. However, there are some people that end up with some very nice ideas. I really like this work about something called like neural tangent kernels. And actually, there is a full line of work which is using those ideas, and it is as follows. So you can consider like a neural network, so it's exactly the same as before, except that there is this small renormalization by 1/square root of the width of a layer. So it's the width of the output, not of the input. The renormalization will change nothing further forward. Like it's okay. If you take a row here, it's homogeneous, so you can just remove all the constants here. However, it changes everything for the gradient and for the optimization of the model. And if you assuming that you initialize everything as a Gaussian, fine. It's going to behave as the width is going to infinity, and actually the ways you have the convergence is by the first layer has to go to infinity, second layer, then the second layer goes to infinity. So some guys improve it and show that if every width is larger than some values, you can get some bounds. But like, let's keep to this way of converging. You get actually very easily that the fact that the output of your neural network will really be similar to a Gaussian process. So here it's like, it's it's obvious. It's just the output of it's just W0 of X0 renormalized to get there. And so each row of the output is a Gaussian with this covariance matrix. And actually, if you iterate this idea, you can prove that each layer of your neural network is going to have a distribution that is a Gaussian process. And the proof is, quite straightforward. So if you take like two layers, right? Just write the definition of like the iteration of one layer over 0 there. And so if you fix like two dimension, what do you get here? You get like, here's this Diane matrix, which is basically the covariance matrix of a white noise, great, so it's the identity. If this guy is going to the infinity, then you know this is behaving like the covariance matrix of the Gaussian process of the previous layer, and so you get by recursivity the fact that, well, you get this kernel here. So if you're not convinced, I swear, like, literally write it down. Like, I would like to finish the talk, so I'm not going to make it on the breakdown. Only the element of the proof is here. This being said, people have, so I mean, it was the work of Jaco et al. If you assume that your layer is your neural network is real valued, you can introduce this neural tangent kernel, and this neural tangent kernel is exactly determining like the dynamic of your neural network. So if you compute the, if you assume that you're training with, for example, this expected measure, I mean this subset of the data set, your neural network. So assuming it's a full gradient and not SGD, but like, you know, it can be adapted to SGD. If you write the dynamic of your neural network, you see that this guy is going to depend upon this kernel, where there is this moving term CW of t, right? So it's just a gradient, right? You just write the equation of the gradient with the loss function. Super. And you can prove two things. First, in the infinite width limit, this neural tangent kernel, which is literally like the dot product of the gradients, is going to be deterministic. So it was a bit expected given like the previous formula, right? But like the most interesting thing about it is that it's actually constant. And this is super surprising. Because, and the fact it's constant is because like the weights are going to the infinity, and this model is going to behave like it's linearization. It's not trivial. But the fact it's constant, it means that, for example, if you use a mean square loss, like just a quadratic loss, you get a linear model, right? Everything is linear. It's constant. It's just a giant matrix, which is fixed. So you get a linear model. So this is great, because like we know how to analyze that. There is an exponential of something, which is going here. And you can prove that if you use a Rolu kernel, A is going to be a semi-definite positive. And so in this case, you can prove that you have this dynamic, which is going to a global optimum. And you have something that behaves like a linear model, which is quite impressive. I mean, given neural networks are highly nonlinear. And this is due to the fact that here the width is super large. So now, some other people, they noticed that actually, this is not something which is specific to a neural tangent kernel. And if you consider another neural network, again, you have you get a dynamic, so here for the linearized model, which is fixed, very similar to the one before with the neural tangent kernel. And you can prove that without the previous NTK parametrization, a standard model is going to behave like its linearization at the moment that the weight, that the width, pardon, of the neural network is going to be arbitrarily large. Okay, so the one explains the other, and actually, this refers to it's a work like so it's mainly Linnaeus Shiza, who's like a mathematician who has driven like most of the ideas are here. It actually like very close to something called lazy training, and it's super interesting. It's the idea that there is an implicit bias of the gradient descent, which is linked to the way you're going to initialize your neural network. That implies that if your model is too flat, it's not going to move much. And there is a way to quantify that. So informally, you say that there is a lazy regime when the path the optimization path of both the linearized model and the standard model are close to each other. And actually, this does occur at the moment that around the initialization, the loss is moving a lot, but the weights are not moving much. And here there is a Hessian, because if you think about it for the linearization, what is going to move is the Hessian, not the Jacobian. And so you randomize that. So you can introduce like this quantity, and you can show actually that in the two previous work, I've discussed actually this phenomenon of lazy training is going to happen. So it's great. You can have some explicit formula for a square loss. And yeah. In fact, there is a way, like if you have a given model, there is a way to study it in its lazy regime. And it's super simple. You just have like a rescaling factor, and you play with it. Like it can go to 0, it can go to infinity, and with that, you can have your have a dynamic that is going to be closer to a linear dynamic. So you have again some explicit formula for the mean square loss, yeah. So that's a technical detail. It's fine. And so, like the interesting thing about it is that if you take a one hidden layer neural network, actually, you can have again an estimate of the laziness of your neural network based on the randomization factor. So here there is this assumption that you have a Holu which is homogeneous in the parameters. So if you initialize differently than sigma something, your parameters, the scaling factor is going to go in the alpha here. So you can have an explicit scaling factor. And if you consider the initialization as a Gaussian, then you can prove that your neural network is going to behave as its linearization, which exactly occurs in the two previous models I was describing. So, and there is another setting. So you see that this quantity does not necessarily need to go to 0. It's when this stuff is close to 1/m. And this is a dynamic that Linnaeus and Shisa and Francis Bach have studied, and so they got some results. I will discuss them very quickly. And beyond the one hidden layer neural network, you can also apply the strategy to standard neural network, assuming that at initialization you get something equal to 0. Like if you think about it, like there is an alpha term here, so you need to remove it if you want to play with the scaling factor. So this is great. Okay, so I'm going to speed up a bit. So you can prove that you can bound the dynamic of the linearized neural network and the neural network according to the scaling factor. So that just makes sense. So if it's small, yeah, if it's larger, then it's going to be closer to its linearized dynamic. Excellent. And actually, since it behaves very similarly to its linearized model, you can also get the fact that your model is just linear, and so it's going to go to some minimum if you have some assumption on your loss, and it's just a linear model. So then there is this question: is it responsible is this regime responsible for the good performances of neural network? I'm sorry, I'm completely obsessed by those things. Is it working? But the answer is no. So if you take a neural network and you play with the laziness of your neural network, so you just have this alpha factor. So you can verify that your neural network is indeed linearized because you have an explicit formula for the Holu in this case. Well, what you see is that at the end of the day, the accuracy drops. So unfortunately, laziness is great. Like you can study, you can have some study. It's really too bad because the model was linear. It could have been very helpful to get some guarantees, but actually, it doesn't work. Well, would have been too simple, right? Okay. So then, right. So yeah, now I'm not going to discuss that. And beyond, so there is something it's against because everybody discussed it. So I'm sure everybody has seen this neural network, universal approximator, blah blah blah. Well, everybody knows these kind of things. There are some bounds for some estimation approximation bounds that you can get in the nice work of Baron. But basically, there is a smoothness constant, which is given by the Fourier transform of your neural network. So that's really the take-home message on one hidden layer neural network. And I'm trying to finish in time. So, so there is a very nice point of view by Francis Bach in his breaking the curse. I really love this paper, breaking the curse of dimensionality with convex neural network. And so the idea is to view. So there are several ideas, but like the big take-home message, like if you forget every slide, it's the fact to write a one hidden layer network as an expectation of our measure. I know at the moment you say that, and you see that a finite neural network, it's as if like there was a discrete measure associated to it. Then you can define a reproducing kernel Hilbert space. You have some nice approximation properties. So for example, so in the case d equal 1, everything aims at doing some Fourier series. So I wanted to do that, but like I was too slow. And you can prove that you got some Lipschitz function. This is a reproducing Hilbert kernel space. And so everything is super standard in Fourier. It's with a Poisson kernel, so we just have some Fourier results. And so I will almost finish with, there is this beautiful result by Lina Ikshisa. So who has proved that if you take a layer with an infinite width under extremely reasonable assumption, assuming that your layer has infinite width, you have a convergence, which is guarantee of the Wasserstein flow of your neural network. So I'm not familiar, with optimal transport, so I cannot talk as an expert, but I really encourage you, if you like this kind of PDE, I really encourage you to check this paper. It's like the result is very great. So I'm really mentioning it because it's really worth to at least check it to see. That's the best result we get. We have about the training of one hidden layer neural network. So I really encourage you to check this paper. Unfortunately, it doesn't give anything like, finite width neural networks. And okay, from what I was saying, like it sounds like one layer neural networks, they're great because it seems to work everywhere. Actually, this is not the case. You can prove that there is a measure and a function that if you try to approximate it with one hidden layer neural network, you will need an exponential number of weights. If you do it with 2 layers, you will just need a polynomial number of weights. So the proof is quite complex. I was hoping someone will find something simpler, but the result is super interesting. It explains why depth can be helpful. I'm not saying like it's happening in any neural network, but like just an example where depth can be helpful. Voilà. So to finish, like for tomorrow's lab, I encourage you like to so first of all like to download like the notebooks and to try the tutorial on CIFAR10. I will assume that everybody is able to train a neural network on CIFAR10. So please run it, like it's just a click thing. And once you get that, normally there is not much code in the other notebooks. Voilà. So in conclusion, I think deep neural networks are like pretty difficult to analyze. Like, it's very hard to get any guarantees. But I think it's really like a super exciting field. Like there are really many things happening. Voilà.